the world is led by models and structuration in medicine. And this world is led by this since 50 years. And since 50 years, we are building models, we are structuring data, and we are building models, and we are structuring data. And since 50 years, we are struggling at being able to share data. And we usually see legal framework as the reason why it doesn't work. And we have a lot of good reasons to explain why it doesn't work, but we basically never question the use of models and structured data, which maybe is the problem, actually. So this is my team. I will show it again at the end. And it's getting very important because, as you know, data is now a market. It's not just about research or governance or just helping the care system to work, like planning and billing and whatever. It's a market. Data has a value. And I will not go too much into this because you know data has a value, and this is one of the reasons why NFDI4Health exists, because data has value. Data has also a cost. And very few people speak about the cost of data. And this is a paper you can see. I will not enter into the details. You have everything to find it. But more or less, if you take that paper and you look what it represents in terms of costs for a university hospital in Switzerland, and this is CHUV, and you take the salaries of people at CHUV, and you more or less take every university hospital in Switzerland, and you look at the cost on a yearly basis, it's between 400 and 600 million per year per university hospital. This is the cost we pay people to spend time on computers entering things which are not directly used for patient care. But all the rest, important things, logistics and all what I said before. So there is a cost to the data, which is not about privacy and legal and ethical, just financial cost. So the data in I should not see my slides because I will mix between French, German, and English, and this will become difficult. It will be exactly like the problem of models. But let's go back to the text. The data in medicine and in healthcare in general, they are really not comparable to most of other domains. They are very heterogeneous, you know that. Most of their value is in temporality, the time it has been acquired, the evolution of the data. It is also at one point of time, like X-rays or lab at a given time, but a lot of the information and the knowledge of the data is in the time. It is multimodal, and this is my data, so I authorize me to show you my data. So it's real data, it's very multimodal. And this is a mammography. So in Geneva, most mammographies, they have 9 million pixels, and every pixel has 5 variables, 2 for location and 3 for the luminance and the color and such type of things. This is a lot of data. And all these data of this mammogram, they have been taken at the same fraction of time. And it's complete. Can you imagine a radiologist or a sonologist having to interpret this mammogram if 99% of the pixels would be missing? Just less than 5% of the pixel present. and the rest is absent. It looks like science fiction. The radiologists, they would just not accept such a mammogram. But this is the case with clinical data. Spärlichkeit, Sparsität, they are sparse. And if we take the about 400,000 variables we have in our 11 hospitals, less than 5% of the variables are documented in any one of unique patient we have in our database. And we have 1.7 million patients. None of them has more than 5% of the existing variables documented. And I don't speak about temporality. Just we have a data anywhere in our 25 years history for this variable, for this patient, less than 5%. If we look at the evolution of KISS, and when I speak in German, I say KISS just means Kiste, data Kiste. It is mostly aesthetic surgery. You have 40 years difference between these two systems here. And except with what you see, and it looks much better, it's surgery, it's aesthetical surgery, cosmetic surgery. The content in terms of informational content, there is no change, no evolution. Check boxes, radio buttons, age, short text, numbers, integers, booleans, no changes. And that's the real problem is that when we do categorical data, and we mostly do categorical data in the clinical representations, we actually damage a lot the information. And you probably all recognize this picture on your left side of the image. It's one event in a story. White snow, poisoned, surrounded by mourning dwarfs, by the 7 mourning, actually 6 here, but there is a 7 somewhere, the 7 mourning dwarfs. We all know there are 7. We don't need to count and see that there are only 6 on the image. There are 7. And this you can write in French, in German, in English, in Chinese, in whatever language, you can write it in a text. And then you can code it in ICD-10, ICD-11, ICD-12, ICD-14, ICD-16. In any type of these things, you can code it. And you have the codes. And the codes here, they have been done by the supercoder of HUG, who are doing the coding for billing. So they are good at coding. We can understand how we can go from the image to the text to the codes. But I hope you can understand that you cannot go from the codes to the text to the image back. This is a road you can take only in one direction. Because there is a huge information loss between these three informational contents. And if you think about patients, it's exactly like the image on your left. It's one event. Is it a outpatient visit? Is it a inpatient visit? Any type of encounter? It's an event in a story, the story of that patient, the life of that patient. So this is really a kind of metaphor of the electronic patient record on medicine. And unfortunately, this metaphor has a reality in information loss. When we do use models, we do the same. In addition, we do another type of information loss and information compression with loss, which is we decide how we organize this information. And here you have an example of a pine piece, and you have a picture of it. And on the other side, you have a kind of model representation of it. You have the part of the pine, how many parts, so many parts, 5 parts, and you have on each, you have needles, and you can count because you decide this is important, is how many parts and how many needles per part, and you count how many needles per part, and you represent the parts, you represent the needles, and you have a model of the piece of your pine. So not only we damage information because we categorize it, but in addition, we damage information because we model it. So I would like us and you to think about killing models and killing structuration, which, especially for German people, but not only, it's for the world in general, is something which looks like not just eccentric, but really, you should burn this guy. Because we are all fighting for more structure and more models and so on since 50 years. But we failed since 50 years. Well, what we did in Geneva, and it is what was supposed to be the SPHN strategy, which was not applied like that, but we did apply it in Geneva on a very strict manner, is that we looked at the existent structured data in our database, and we have 25 years of full data in our 11 hospitals and 40 outpatient clinics. It's all the state of Geneva public system. And the data in the structured database, we have one huge data warehouse, which is a NoSQL database. And in this NoSQL database, every up to 3-4 minutes, every primary source of all the care system is dumped on it. So it's always up to date, more or less, well, 3 minutes maximum. And you have piles of data, which are all in, it's a NoSQL database, a MongoDB, it's very similar to text files. All the structured are transformed into string representation so that you can basically put anything on it, anything. And we have anything. So we tried to understand which type of data we have, what are these data, and to put semantic on it. And we have tried, it is a work that started 15 years ago. We have tried to use lots of automatic approaches. And finally, none of them were really working because in the database, for example, for categorical data, what is stored is usually the index of the item in a list or a checkbox or groups of possibilities, so that you don't have acute myocardial infarction or I don't know what. You have 0, 1, 2, 3, 4, 5, because the clinicians have selected the third item of the list. So what you have here, millions of lines of 0, 1, 2, or 3, or 4, or 5, or 6, because there were 7 elements in the list, and people have chosen 1, or 0, or 1, or 2 of the element in the list, and you don't have the text of the item, you have the order, the number of the item, and so on, and so on, and so on. And so this had to be done manually. And manually, people have opened the original system to see in the computer what was written in the list, in the title, or what was written on the web page, such as when the background is green, it means this is about the pregnant woman. When the background is yellow, it's about the obstetrician, and when the background is I don't know what, it's about the Frau, la sage-femme, I don't know how to say in English. And this is not in the database, this is in the screen. So they translated all of it into something which I will speak later. And this ended up into a huge acyclic directed graph, a disconnected acyclic directed graph. Millions of small graphs starting with maybe one or two nodes, and the largest maybe some dozens of nodes, and millions of these things, which didn't represent the data themselves, but the way the data were represented in the structured database. And these things, if you take SNOMED, if you take ICPC, if you take ATC, if you take ICD, if you take all these things, they have labels in French, in German, in Italian, in many languages. And this gave us the base to build automatic pipelines to do the same work on text. And this is the point two. And this on manually done structured data and automatically done on text, it gives a pretty precise expression of the semantic of what is structured and what is in text. And it all builds the same acyclic directed graph. And when you look then at the data themselves, which patient has which fields or which concept documented, it gives you a probabilistic graph. So you have two graphs, one which is an acyclic directed graph, and it's not a knowledge graph. It's a little bit more complex than a knowledge graph, and you have a probabilistic graph. And then only you can map the graph to any model like OMOP, CDISC, whatever. But this is at the last stage. Before mapping to models, you actually just represent the semantic of all of it. So this is not so important, but there is some information in the open data. So how did we do that? Is it SNOMED? What is it? So in fact, it's not SNOMED. It is SNOMED, but it's not SNOMED. It is what is important is that we use a formal descriptive grammar. SNOMED, let's start like this. French is a language. It's a natural language. German is a natural language. Natural languages, all of them, they are built with two objects. They have a vocabulary, they have a vocabulary, and they have a grammar. So, Deutsche Wortschatz, le vocabulaire français, et la grammaire française, grammatique. And you have the two objects. So we know that, I don't know why it moves along. I don't know. We all know that the vocabulary of SNOMED is not enough. We cannot represent everything with the vocabulary of SNOMED. There are many things missing. So if you say this old woman has SARS-CoV-2 Omicron B11529 infection, you can represent with SNOMED old women, you can represent SARS-CoV-2. You cannot represent Omicron because this is the WHO classification. And you cannot represent B11529 because this is the Pango concept. It's a Pango element of the variants of pathogens and all these things. And you have 350,000 concepts in SNOMED. You have millions of variants in Pango. So never Pango will be downloaded into SNOMED with new SNOMED codes and whatever. But it's like in German, in French, or in all languages. We use vocabulary. We use vocabulary from other languages. SARS, COVID did not exist 5 years ago. Now it exists in all languages. We add all the time new elements. And in the language which is spoken in a city where I grow, Biel in Switzerland, you mix French and German, and you can say c'est le fâtre qui a schlagué le cat parce qu'il a piqué du speck dans le frigo. You probably didn't understand that, but it's a French grammatic, and it mixes French words and German words and Swiss German words. And we all do that weekend and sandwich and cool. Es ist so schon cool gewesen. Cool. What does it mean, cool, in German? So we constantly pick words in other languages, and we don't need to wait 5 years until SNOMED International accepts the words and gets a number and so on and so on. This is too slow for the evolution of science, of medicine, of what happens, of what we have to do. So we took the grammar of SNOMED, because SNOMED is a grammar and a vocabulary, concept and how to do post-coordination, like French and German and Italian and blah, blah, blah. We took the grammar of SNOMED and we extended that grammar pretty a lot. And I will give you some examples. I will try to give you some examples. So that at the end, we can express a lot of things using that grammar, using many different vocabularies, like SNOMED itself, but like others, ATC, Pango, any WHO thing, Wikidata, any external vocabulary. And we defined a set of properties that these extensions need to have. And we defined some properties that the vocabularies must have. And as long as these properties are verified, we can use them. And what we did is that we demonstrated that you can parallelize the work. You don't need everybody to agree on everything. You can have different people working at different places at different times without knowing each other, like we are able to learn English without being all together at the same time when we do that, without having some academy that is deciding every day which words can be used, how is it to be used, and so on and so on. So no central coordination, but a formal grammar and a set of vocabularies. And doing this with very few resources in not that much time, we did that, what you have on the screen. Oh, there is still French on it, sorry. But basically, we have 1.7 million patients in our database. We have encoded about 80,000 variables. It needed about 40,000 concepts, so to say. And today, we have 12 billion data points, which have a very precise semantic in the structured, the so to say structured database. And this is more than UK Biobank. And we have in the database 80 million documents. We have automatically analyzed 2 million of these 80 million. And with these 2 million documents, which have been annotated automatically and produced a JSON representation of the document without identifying information, well, not without identifying, but with metadata telling what is date, what is name, what is whatever, everything. And the concepts, we have text, which are automatically annotated for IPA and for semantic. And these texts represent 1.25 billion words. And this took a few hours to do with the pipeline. So I will stop here. I will just show you, I asked one of my team member this morning to send me some example of the database. And I will also share you this just so that you can say it's kind of not completely real time, but it's almost real time. I hope you see my screen. So you have an example here where I suppose you see my screen in dark.
Yes.
So what is written in white is what can be done with SNOMED. What is written in green is the extension of SNOMED which we have done. And what you have in red is the real value of the patient. So you see, for example, heart rate, quantity attribute 204 units beats per minute, maternal hypertension syndrome disorder, and treated with ephedrine. So there is no treated with attribute in SNOMED, but you have ephedrine, and you have, or maybe you don't have ephedrine because it's a substance, and you have a maternal hypotension. You have temporality. Here, an example where you have this, a follow-up consultation procedure. It's in white, so it's full SNOMED. But the date of that outpatient visit, you cannot put it in SNOMED, but you have, we use an existing date attribute, and we have now in red a value for that attribute. And here, and this should be in red, the PANGO, you have an example of a severe respiratory coronary syndrome. It exists in SNOMED, but what you cannot say in SNOMED is that the strain is PANGO B16172. And this is the extension. And with this, we have a formal grammar. It's a grammar with an extension of what exists in SNOMED, because you can have additional things. And these additional things, they include negation. This is an example of the negation where you have repair of the umbilical hernia. It's a procedure. It exists in SNOMED. But what you want to say is that there is no mesh that has been added to that reparation. So you want to say without a mesh. And SNOMED actually does not support negation. It does not support scalars. It does not support temporality. It does not support real values. It does not support external references such as PANGO and so on and so on. So, voilà. And this is the example. And I hope we can now discuss a little bit about what I am trying to convince you to do. Maybe just one point. I was lastly on the MDM that website from this incredible work which Martin Dugas did put a lot of energy in, and it's really something incredible. But maybe what is also a learning from this is that now you reach with it more than 25,000 medical models. And I think this should also help us understand that it's not something that is sustainable. We will not be able to continue growing, adding new models, adding new micro models, nano models, managing all of it, mapping between every of these things, and it maps not completely, and blah blah blah, and they evolve, and we need uh, to do that well model cycle management and so on and so on. And when you just see OMOP, the MOP CDM, you have the version 5 with a lot of tools, Atlas, and so on around it. And since a few years, we have the version 6, and there is no tools around it. It doesn't work with the 5. And since several years, everybody in the community is waiting that all these tools are migrated to the 6. And it is not migrated. It's a lot of work, a lot of money, and nobody wants to do it, and so on and so on. And I think this is exactly the problem we see since so many years in the field as a whole. We are constantly running behind the train.
Thank you very much for this very inspiring and visual talk.